and we can start now. So hello, welcome everyone to SD Skills Online Meetup. If you are new and you don't know what this group is doing, please message and I will share you some information. Please, if you are not active on Slack, please join Slack. There are a lot of things happening there. You will find about all the online activities that we are doing, all the other meetups that we are doing online. And today's session will be hosted by Naga. Naga, up to you.
Okay. Hi guys, this is Naga. In the past, like last year, I have presented few sessions on different coding and system design. Today, we will go through some of the recursion problems. So before getting into this, I have 4 problems. At least like before getting into this recursion, I would like to at least refresh like how we can get the recurrence relations and at least identify the time complexities for recursion problems. I'll probably refresh people's memory through some of my personal notes. So as I hope everyone can see my screen. So like at least like one of the 3 major methods for solving recursion methods is we decrease the problem scope and conquer the problem like till it hits the base case. So normally like for recursion we need base case and the minimum to solve, and there are like various methods of reaching the base case. Like so the first one is like decrease and conquer. This is like every time you go 1 or 2 steps decrementally and till you hit and you come back. So another approach is divide and conquer, like you exactly split every time like by half or by quarter, like depending on the problem. And other famous is backtracking approach, where you explore all possible permutations or combinations depending on the choices that you have and to find a solution. So I'll quickly show the 1 and 2, how you identify the time complexities. For backtracking, I think anyway it will be depending on permutations or combinations. You need to find the, depending on those formulas, you'll find the time complexities. I just have few examples here just to make people understand. The first one is like decreasing functions, which is decrease and conquer. Suppose let's say you have a function like this called test, which takes n argument, and as long as n is greater than 0, it prints something and it calls itself for n minus 1. As you can see, every time you decrement this, like you decrease the scope by -1. So we all know that this clearly runs n times. So how we represent this function in terms of recurrence relation is this, if we take this test function as t of n, t stands for time taken by this test of n, and this you are doing tn minus 1 in this line, and this is you can have many more lines like system.out.println, but as long as you don't have loops, you're just doing something or printing or storing, then that means like a constant. So instead of, it doesn't matter whether you represent 1, 2, 3, 4 depending on the number of steps, but for the simplicity's sake, all the constant can be represented by 1 in relation. So here the time complexity of this kind of decreasing function is big O of n. So that's pretty straightforward. So as you can see, I just modified a little bit to add a for loop inside the same function. Every time you, as long as n is greater than 0, you again go to n steps and do something. And this itself is like big of, I mean like n times you are doing. and here you are decrementing. So as you can see, the time taken by this T of n is equal to T of n minus 1 plus n. In this case, the time complexity will be n square. This also like can be easily identified. So another thing that you notice here, it is very similar, but every time I'm multiplying by 2, I'm going twice so fast as normal. In that case, this for loop will be log n, as you can see. So the time complexity will be for this n, and this is log n, so it will be n log n. So this, like I just listed few more recurrence relations in a similar fashion. And if the recurrence relation is this is n, this is n square. And if you are decrementing by 2 every time, then it's almost like n by 2, which is still represented as O of n, because this constant is negligible. So even if it is 100 instead of 2, and then if you are doing n steps, so it will be in the worst case n square. So if you have n square here and you are doing like decrementing 1, it will become n cube. So this is just some kind of different functions how you represent, and the main idea of any function that you write is to represent in terms of recurrence relation and then determine the time complexity from that relation. So as you can see, you are going 2 times for every n here. It will be 2 into t n minus 1, which is equal to 2 to the power of n. If you do one more time, like if you add another one, like every time for n, you explore the possible approaches, then it will be 3 to the power of n. So just to
Naga,
refresh.
one clarification.
Mm-hmm.
Can you go up where we had the first exam? So normal, yeah, little bit up.
Mm-hmm.
Yes, so this one, the yeah, below one. This one. What was the complexity here?
Log n.
No, not this one. The one above, where we said that it is n square. I guess. Yes,
Oh
this one.
yes, this is n square. Yeah.
If this is n square, then
Mm-hmm.
the below where we do 2 times,
Mm-hmm.
why it is 2 to the power n?
No, this is not 2 to the power of n. This is n log n.
No, not this. The
Oh,
one
okay,
that you
okay.
are talking right now. When we are doing 2 times, we said that this is 2 to
Oh,
the
okay,
power
okay.
n, and
So,
that
so,
was
so, yeah, the idea is you are calling, we are just representing this function as t of n, right?
Mhm.
So you are calling this same function with n minus 1 2 times. It's basically for every one step of this t of n, you are exploring this, the same n minus 1 2 times.
Mhm.
So that's why it's 2 into n minus 1. But in the other example, we are, this is not a function, right? This is,
not
this for
not
loop
this
is
one.
not a,
The above one above.
oh,
Yeah.
sorry. So this one is not a function. You are just looping from 1 to n.
Oh, I see.
So,
Okay.
um, so this is s, not like it's not expressing in terms of itself, right?
No, no.
So this is part of the.
Yeah. So my question is, when Tn is equal to t of n minus 1 plus n,
Mm-hmm.
then it is O of n square. But if Tn
Yes.
equal to 2Tn minus 1,
Mm-hmm.
then it
Yeah.
becomes to the power n.
Yes. Correct.
Okay.
And there is a master's theorem which I have at the end, so using
Mhm.
which we can compute all this. I mean, like
Okay.
I'm just showing some examples before showing the master's theorem. So for this kind of.
I think at the high level, correct me if I'm wrong, Naga here, but the way I'm understanding this is if we are trying to iterate like recursion, like the T n minus 1 is capturing the recursion part, and the
Yes.
n or n, that's more like iterative, like the code, like order
Yeah,
of.
yeah, whatever the code that
Right.
takes normally
So,
in the
yeah.
function.
So the way Naga said, right, for n equals 1, if we have a recursive call, then essentially for that value of n, we are doing that many recursions. So, and that's why it's like 2 times. that, and like even if we substitute values, I think it kind of gives some idea, but the exact thing would be.
Mm-hmm. Yeah, I think if we look at the Master's theorem later, it will be clear. So if you have another one here, like test of n minus 1, I mean like that will be this recurrence relation, whatever I have, like 3 into tn minus 1. So if you have 2tn minus 1 plus something, so this means 2 to the power of n and multiplied by this. So here we had 1, that's why like multiplied by 1 means same thing. So this is the Master's theorem, which expresses all the equations that I have given, all the relations that I have given previously. So the Master's theorem states that T of n, which is time of n, is equal to a into T of n minus b plus f of n. This f of n is whatever the loop or constant that you normally do. So here a is actually greater than 0. In some cases we have seen it is 1. So it's simply like T of n minus 1 in the previous examples. So if you so b is again like 1, at least like greater than 0, and then f of n is equal to n to the power of k. This k is again greater than or equal to 0. So now we can actually substitute some of these values into this and see what equations we'll get. So this Master's theorem actually have 3 cases where a is actually less than 1. This a is less than 1. In that case, whatever the time represented by this f of n, that itself will be the time complexity. In this case, f of n is big O of n to the power of k. So that itself will become the time complexity. If a is equal to 1, then in that case it will be like n into n to the power of k. This is f of n, which is represented as big O of n to the power of k plus 1. If a is greater than 1, in that case it will be big O of n to the power of k into a to the power of n by b. So let's take some of this example. If we take a is equal to 1, we can see so in this case you can see a is equal to 2 and b is equal to 1 and f of n is equal to n. So if you take this, a is actually greater than 1 in this case. So you can see that this represents this formula. So here a, if you see f of n is equal to n, which is n to the power of 0, which means that k is equal to 0. And sorry, I think n to the power of 1. So that's why k is equal to 1 in this case. So n to the power of 1 into a is actually 2 here. To the power of n. n is, what is n here? Yeah, n will be as it is, n by b. So b is actually 1. So n by 1 is again n. So this is the time complexity, as you can see, n to the power of 1 into to the power of n. So the other example, if you see, so all this, this is an example of second case where a is equal to 1 and b is equal to 1. So a is equal to 1 and b will be again equal to 1. So in that case, we go n to the power of k plus 1. So the k is here 2. So if you see in this case, n to the power of k is equal to 2. K plus 1, so it will become n cube. If you explore like all the scenarios, you can easily get, like if you remember this theorem, like we can first express our recurrence relation and find the values, and accordingly we can find the time complexity.
Naga, can you please do the first one where I had doubt with this?
Okay.
The
A is less than 1, right? So where A is 0. So let me see if I have a
no,
scenario.
not this one. The one that I had a question, right? The one before. Yeah, still the first. I think this, not this
This one?
example.
So
Yes,
here A is 1 and B is 1 and K is also 1.
all are one. Okay. So if you can put in that formula, A is 1, B is 1, and K is 1. So if you can go to the master theorem and put the formula. Okay. Yes.
So let's put A is equal to 1, B is equal to 1, A is equal to 1. So if A is equal to 1, it falls into case 2, which
Right.
is go of n to the power of k plus 1. So in that case, k is 1.
Oh, yeah. Okay.
So it will be n square. Yeah.
Okay. Makes sense. Sure. Thank you. I don't think so. Do we have an example of A less than?
That's what I'm seeing. I think
Maybe that
I
divide.
don't have an example here,
Okay. That's
but
fine.
yeah, I can find out. I think. I think maybe no. This here also we have it's A is 1. I'll actually try to find, but like if we try to, in that case it will be n to the power of k. So whatever f of n is, that will become the main time complexity. So I'll actually go to the next step because we'll need at least some time for solving problem. So recurrence relations for dividing function. So this is kind of a divide and conquer. It will be similar to the previous approach, except that instead of decrementing here, we will divide the main problem scope by a certain number. So if we, in this case, it's like n by 2. So every time we are dividing the problem into half and doing something constant time. So it will be expressed in terms of time taken by function test of n is equal to n by 2 plus 1. So in this case, it will be log n. So we all know that like this is the approach taken by binary search and heaps or whatever. Like we and if we have a similar example, like we divide, in addition we do something on n times. Like here.
Just one question.
Uh-huh.
For the previous one, can we just apply that function what you had the master's theorem for log n?
No, this is a divide and conquer, right? It's different from decrease and conquer.
Okay.
So we have a different master's theorem for this.
Okay, sure. Got
So
it.
I'm just showing the time complexities. So for this also we have some master's theorem.
Okay.
Remember.
One more question. So the second line where you said t of n by 2 plus n.
This one.
Yeah, it should be n log n, right? The time complexity.
Oh, yes, correct. I think it's my bad. Thank you. So this is the login and this, I think, wait, let's come back to the master's theorem and wait, I might have done mistake. It may be, or I may have it here. No, no, I think that is still n because you're dividing exactly half, right? It will be like n plus log n. So we will ignore log n in this case because n is greater than log n, right?
Oh, okay. Oh, yeah. The previously we were treating plus as a multiplication. So I
yeah. So this here we have a different master's theorem. We will go to this example also and see how we will get the values. So I have another example where you have a function p of n where we are dividing by half, but we are doing 2 times. So this will be something similar to chart, like you go left and right, like you divide and go once on the left and once on the right. And we also do something on the n times, it would be something equivalent to merge. So here the recurrence relation is 2 because I'm actually doing 2 times in terms of the same test, and I'm dividing by 2. So 2 into n by 2 plus n. So this complexity is n log n. So here the idea of Master's theorem is little different. So it won't be like plain multiplication like before. So I have many examples down. First we'll look into this Master's theorem. So Master's theorem again, like here is simple like or similar, except that instead of n minus b, it will be n by b, and you have an a and function of n, where a is greater than or equal to 1 and b here is greater than 1, which means that at least 2 or more. And this f of n is expressed in terms of n to the power of k into log of p and n. We will see what this is and how we can determine this p and all, p, k, everything. So we have 3 cases here. So this log need to actually find in this example log of a to the power of b. So a is this and b is this. We need to determine the log of a to the power of b. I will show the examples just below all these cases. First we'll actually look into the Master's theorem. If log of a to the power of b is actually greater than this k, whatever that we have in f of n, so then it will be like n to the power of log of a base b. If it is equal to k, then we have 3 cases depending on this p value. So again, I'll tell you like how to determine the log p, the p value. So if p is greater than -1, then this is the time complexity. If p is equal to -1, then this is the time complexity. If it is less than 1, it is we will just ignore all this log stuff because it will be too many logs. We'll just take n to the power of k. And if this is less than k, then we have 2 cases. One is p greater than 0, and in that case this whatever we have in f of n, that will be the time complexity. If it is less than 0, we will ignore this log and just take n to the power of k. So let's take an example of case 1 where I'm saying log a to the base b is greater than k. We know that this is a here and this is b. Sorry, this is b. In this case, I have f of n as 1. So the f of 1 can be expressed as n to the power of 0, which is again 1, and log to the power of, like 0 base n. This will be again like some 1. So if you see, this is n to the power of k. So k is 0 here, and this is p. P is again 0. So the log of a and this is b base 2 is 1. In this case, this value is 1 and k is 0. So k is n to the power of 0, n to the power of k is 0. So this condition is met, like 1 is greater than 0. Then this is the time complexity that we actually did, right? This log of a base b, so a base b base 2, which is 2. Log of 2 base 2 is 1. It will be this whole thing is actually 1. In this case, time complexity is big O of n. We'll look at another example in the same case 1. In this case, I have 4 times. Like if whatever the expression here, we went 2 times, right? Like if you similarly, if you have to do like 4 times, and still b is 2 and f of n is equal to n. So in this case, like as you can see, A is 4, B is 2, and f of n is equal to n. So n to the power of 1, which is k is equal to 1 here, log, since it's only n, so this is still p is 0, so that will make it this one as 1. So log 4 base 2 is 2, so which is log a base b is 2 here, and k is 1, so 2 is still greater than 1. We will apply the same formula again and get n square. So similarly, if you do 8, it's basically log of a base b is actually you will get 3. So it means n cube. So this is mainly driving the factor. So we will actually look into case 2 now. So case 2 example is recurrence relation of A is 2 and B is again 2, but f of n is equal to n now, which means that k is equal to 1 and p is 0, which is greater than minus 1. So in case 2, let me show you just to refresh. If log of a to the power of a base b is equal to k, so k is 1 here. So k is 1 because like n to the power of k, this is n. So k is 1 and log base 2 is 1. So they both are equal. In that case, again we have 3 subcases. So p is greater than minus 1, p is again minus 1 and less than minus 1. So if we substitute the values, sorry, I think I went a little further. So k is equal to 1, p is equal to 0, this condition meets. We just take the formula from there, and which is n to the power of k is 1, and log of p plus 1, which is log 1, the base n, so it will be log n, n log n. For this recurrence relation, it is n log n. Some of the recurrence relations maybe we can just see, and this is the regular formula for merge sort, right? So we just know that it's n log n. You just need to use this only if you can't, if it is not very well known recurrence relation, then only you can use this formula and try to substitute the values and see. So here log n by log n. In this case, p is equal to minus 1. So since it's in the n by log n, so if you take log to the top, like n into log to the power of minus n, that's why in this case it will be is equal to minus 1. In this case, whatever the result that we have, it will be log of log n. Similarly, there is another example. I'll share this sheet also. You guys can go through, and there are actually proofs to prove that through induction method or substitution method. You can actually prove this T of n, this relation meets this time complexity by actually going through some proofs, mathematical proofs. So that is and all, like it's too much. I don't know if how many people will actually ask, but it's good to actually listen and watch. I can actually, there is a good lecture called Abdul Bari. All these notes actually were based on from his lecture. I'll share those videos if you are interested in proofs for all of this. He has clearly drawn each recurrence relation in terms of recurrence tree that we normally explore, like a tree format to understand better. And also he has explored to like mathematical induction proofs for all of this. So with this, let's get started because it's already 2 on some problems. I'll share this sheet with you guys later. Any questions before we jump on?
Naga, this is Supriya.
Yes.
Naga, I think one of the participants actually asked how does that become log n? I think it was an earlier example where you said she suggested it was n log n, but then you said it probably is just n and not n log n.
Yes, correct.
I think somewhere above. Can you explain that now, if it doesn't take too much time?
Let me see. It's in
Yeah, I think it was that
decreasing.
one. No, go up again. Oh, dividing functions, is it?
Yeah, this is in dividing.
Yeah, so I think the second one here, just the t.
Okay, I got it. Let's take this and see which example it falls into. I think I may already have covered this someplace. Let me see if I have covered or not. If not, I can actually see which case it falls
Yeah,
into.
actually, there were two examples. One was the one that Supriya just highlighted, and then there was another one where we took actually n log n.
Mm-hmm.
Sure.
So A is equal to 2, B is equal to 2. So the f of n is equal to n to the power of k. Let me actually write this. This is the formula thing. So this one, right? So now k is actually 1 here. Let me. So k is 1. Sorry, I think I screwed up something. K is 1 and this p is 0. So k is equal to 1 and p is equal to 0. So this falls into which case? Log a base b. So log of a base b is 1 base 2. Log 1 base 2 is actually 0. And this one 0 is actually less than a in this case. K is 1. So k is equal to 1 and p is actually greater than or equal to 0. It falls into this equation. So in this case, we already have n to the power of k. K is 1 and log 0 of n is actually 1. So it will be big O of n.
So log of 0 to any base is 1, is it?
Yeah. So
okay. I'm not sure of that part. I thought log of 0 is undefined. Probably I'm mistaken.
to the base n, yeah. So this, I think, yeah, you can actually look into the. I'll actually share the Abdul Bari's link where he explained how to prove this. So there, I mean, like it's this one is actually 1. So since we okay, let's jump into the problems. The first one is permutation. So we know, like, this is again an example of backtracking, not on any, it doesn't fall into the decreasing or divide and conquer. This is like permutations, combinations, all this actually is kind of a backtracking method where I don't have any master's theorem there. So for permutations, it's normally factorial. Combinations, we have a mathematical formula, right? It'll be the time complexity will be in similar terms. So we just need to know the mathematical formulas for that. So anyone wants to do this first one, permutation? Like anyone wants to share the approach? I can actually reset this.
So,
or if anyone wants to do this, then actually.
Hey Naga, maybe there's a high level approach. I'm thinking like, is it like that we keep, let's say, first constant, right? One constant and define the permutations for the rest, and then try to add one to it. That would define all permutations with one fixed and rest.
Okay.
And similarly, like, keeping one constant and defining permutations around other.
And next step, so that will keeping one constant and permutations will be these two.
Yeah, right. Yeah. And then similarly in the second next two, you kept two constant and you defined permutations of 1 and 3. Just added 2 to the result. Right.
Okay. So do you want to put down an algorithm for this? Like, do you want to code it, or
this is maybe coding somebody else can try.
Have you solved any this type of problems like permutations, combinations before?
Not really. I mean, I have seen this question a couple of times, but I haven't solved it.
Okay. Yeah, it's basically, yeah, if anyone else also wants to volunteer and share their approaches, I'm open. Otherwise, I can do. Any other volunteers to explain the approach? Okay, you want to code, Sophia, or like you want to try?
Did you ask me, Naga?
Yes, yes.
Oh, not today, please. Coding is a little far away for me, but yeah, I mean, I was trying to think of what Dipi was saying. So yeah, I don't know how she was. I was trying to picture what she was trying to say. Was she trying to say to keep one constant and then, permute the rest, and then keep and then put 2 in its place and then permute the rest, or was she like thinking of keeping 1 and 2 constant initially and then permute only the 3, then go back and then permute 2 and 3, and then go back and permute 1, 2, 3? So I wasn't sure how to do it. I mean, probably you should use a for loop and then call a recursion within the for loop. That's all I can think of for now.
Yeah, so it's basically it's like, since we need to explore all the permutations anyway, we need to go and like for each element you explore the rest. So to explore the rest, we can actually call the same recursive function. So if no one else is volunteering, I can actually write the code. Or if anybody wants to take and try it, I can guide also. Okay, I'm going ahead. So in this case, like as so for all backtracking problems, like the strategy is almost same, where you pick all the elements, and for each of the option that you selected, you again explore all the other given values except itself. So it is basically kind of writing the for loop. So let me actually say, click the result. Just define the signature first. You can also store the current permutation and I think these two are enough. Basically, if
we need two lists, one which has the current permutation and one which will have the remaining, which we need to add, so that once the remaining is 0, we'll end the loop.
yes, Yes, actually, we need the nums. I didn't see. Okay, so the idea is like in the recursion, we need the base case, right? Let's take this always has a current permutation, which so the permutation, since it needs to have all the numbers anyway, if permutation hits, if this current permutation hits the length of the nums array, then we actually hit our base case. So in this case, we just add the current permutation to the result. So we just clone that instead of disturbing the current permutation. And just simply return, else we actually explore all the elements in the nums array. And we just need to make sure that this current permutation doesn't have the numbers that we used. So else we just add the current permutation, whatever the nums, and you continue exploring the rest of the numbers, which is again like calling it self recursively. So pass the result, current permutation, and nums. And since you already explored this, you can actually remove for the next permutations, so that like you explore 2, 3 similarly. So you remove the last one in this case. This is a general, I mean, like similar function for most of the backtracking related permutation combinations. You just need to change 1 or 2 lines here and there. So we need to create the result array here. So, and you just call this permute and pass the result and new of a list here. And then num as is, and then just return the result. Let's see if this works. Yes. Any questions on this?
One quick question actually. You said one way to represent this recursions is following a tree approach, to fill in the values, right?
Yes, yes.
I was trying to visualize it in that form. It's always really
yeah, since it is a backtracking, so this tree will be full tree. So I mean, like let me see if I have a good drawing somewhere. There is some app somebody told. Let me try that. I am actually poor at drawing. Let's take this as 1. If we start with 1, so we can actually take 2 in the next number, or there is a 3, right? So we can actually take 3, since these 2 are the only numbers in this. Yeah, so you have these 2 choices. So similarly, if the first number is 1, and the second number is 2, then you only have one choice left, so which is 3. So in this case, since 1 and 3 are already done, so you have only other choice 2. And so similarly, this is starting with 1. So similarly, since we are actually in a loop, we will also start with 2. So you have 2 options with 2. So you can actually go with 1 in the next, or you can actually go with 3.
Makes sense. Okay.
Again, since you already used 2 numbers, so the only left option is 3 here. And here only option left is 1. So similarly, I mean, like, since this is a small number set, it's easier to visualize. But if the number set is big, it's I think the combinations will get, like, it's a factorial, right?
Yeah.
So with the 3 again, you have 1 option. I mean, like 2 options. So,
so it's like if you look at our solution, so we have, there is one current result and there's like a full result, right? So
this, like, as long as it hits the size, then it becomes one of the result. So every time we actually add and remove at the same time. So if we add, it actually explores in the next time. So you are actually trying to add the number 1 again, but since it's already there, so you are backtracking again. So just continue and use the one which is not there in the permutation.
Okay. Yeah, makes sense. Thank you. Yep.
And what would be the time complexity of this? We know permutation is like n factorial.
Yeah, in this case, yeah, it's whatever if n is the length of the nums array, it will be factorial because we'll explore so many options.
Okay,
and
so it's n factorial for us. For this.
Yes. And I also wrote the same code in a little different way, because in this case, like, it's about like manipulating the permutation, right? So I'll just show like same thing, writing in a little different way.
In Naga, I just have a quick question.
Uh-huh.
So this is like, it's mentioned that it's a distinct integers. So
yes, correct.
So that's why we are checking this particular condition that
Yeah,
particular index value is not present in the R list.
Yes, correct. So there is a next permutations too, which allows duplicates. So in that case, the code will need to be tweaked a little bit. So
okay, so then that condition will not be required for that.
Yes. So there we check a different condition. If it's we need to sort for that. Like, we'll actually go to that problem right after this. Just hold on.
Sure.
So before going to that, I just wanted to show another approach for the same problem. So instead of actually having a current permutation list, I'm actually using the same nums array and swapping the elements, just changing these orders instead of creating the size every time. So if you see the approach here, it just simply swaps the elements. So if the index is same, it doesn't actually swap, so this effect will be nothing. I don't need to check that condition here every time. But only thing is, if the return type was a simple list of integer array, it would have been straightforward. But just for the lead code purpose, like, I actually converted this array to a list. But like, if you were to implement on a whiteboard with the interviewer, you could even change your return types as you wish, right? In that case, you are not actually using the extra memory. So if you swap the numbers apart from, like, for this main result. So this is just one another way.
Here you improved the space complexity.
Yeah, so I actually in the submissions, actually this one came up with 100% speed, but the other one was like around 80%, I think. So if you see 0 milliseconds, this one, oh, not that one, I think. I don't remember which one was better performance. I think this, yeah, 3 days ago, right? So this is a 0 millisecond. So this one is a 0, but the other one is 1. So there is a little performance. The swapping is actually faster than adding to the list.
Now, is it really 0 milliseconds?
I don't know. Like you just need to trust the. So this is they might have all the small test cases may not be large enough because it's factorial, right?
Yeah.
Mm-hmm.
Good. Yeah.
Mm-hmm. So let's try the permutations too, which is almost same except that you will have duplicates here. Okay, so you can see that it's again, it clearly states duplicates, but we need to return the unique permutations. So anyone wants to give an attempt for this?
So instead of storing the value, should we store the indices so that it is unique and we will know whether this element is there or not? Because there we were having the elements.
Suppose if this one is in the towards the end, and like suppose if my array is like 1, 2, 3, 4, and 2, and then 3. So what you are saying now? So you want to store the
indices, yeah. So whenever I'm reading from the array list, I'll read it as an index. So I'll actually go to the array and read that value. So instead of storing 1, 2, 3 as we were storing the array list, which we were creating, we will just add the indices instead of that. So would that solve the problem?
If you store the indices, so then again somewhere if you store the indices, it will be similar. Okay, so you just but what I'm actually so if the indices will be all unique, right? But the problem that I actually want is, if you see in the previous scenario we had like 3 factorial, but in this case it's not returning the 3 factorial output, because if these two combinations you will get the same result twice, 112 112, but I need to return only once.
I get that there is like that together when it comes permutation changes the number of permutations.
Yes, so
they are just asking possible unique permutations, not all permutations.
Yes,
okay.
Correct.
The question is
I think it can be solved like it would be a similar approach as previous one, but the for loop will be on the indices, like that will be an additional parameter which will go in and it picks up the element from the array, the next element, instead of picking the same element.
So you again, every time you are saying in the permutation logic, you want to check every time whether the element is present or not?
No. I mean, I will go. I think the for loop what we had, it won't be starting from the 0 every time, but it will start from the next index which will be passing, and it will go to the length of the array, so that it will maintain the uniqueness of the element even if.
But in this case, though you start in the next position, I still have 1, right? In the previous step you might have added 1 already, but if though you increment your index in the next time, you are still having 1. So what approach can you use to make duplicates?
I think we need to sort it first and treat all the elements as one single entity, because that we needn't keep swapping around. For example, if it's 1 1 2, This 1 1 is actually a single number for us. Treat it that way.
Okay.
Or while swapping, can we check like if both A and B are same and we don't need to recurse that particular node? We will avoid that tree path.
Yeah, but during the swap, you are just already decided that this is a valid permutation. So, I mean, like in the previous approach, I think I don't have that code open.
So one of us was saying that, treat it as a single entity. I don't think we should treat it as a single entity. In the sense that it is not that 1 1 1 has to be always together, right? I don't know what how she meant it actually, but it's like even in those ones, the ones can move around. So when you say single entity, are they you're supposed to look at them in blocks? I don't think so. Even ones can move around. So you sort it and you keep while you're looking for the next number, you check if it is equal to the previous number you have seen. And if you have seen that number, you just skip that because you've already done the permutation with the first one. So you skip it till you get a new unique number.
Yes, correct. Yeah. So yeah, this works actually, whatever you explained. So do you want to try coding it?
Coding is, I don't know. I have a block. Let me see. I don't know. I'll try. I don't know if I'll be able to.
I don't know if I can give control from my screen, but like if you have a lead code open, you can try, right? You can share the screen and start trying.
I have to open lead code. Let me see, Naga. I'll see if I can try.
I mean, like the approach that you explained, like it will be similar to the previous code that we have seen, except that you said like sort, and that will make duplicates align next to each other. So if the element is not equal to previous, then you can proceed to this permutation again, backtrack and explore other options. Otherwise, like if there are duplicates, you can continue ignoring.
Right.
Or like if it takes some time, like I can quickly show some how I have one lead code link where it explains all the backtracking solutions. So I can explain and maybe you can try coding next one at least. Okay.
I am hesitant, but I'll see. I'll try. But I think you should explain for now.
Okay. Do you want me to proceed explaining all the solutions?
Yeah. Okay. Please.
Okay. So there is a post like which clearly distinguishes all this backtracking questions. I think some of you guys may already seen this. So this subsets is one another similar problem, but instead of 1, 2, 3, you just list 1 and 1, 2, or like all possible subarrays. As you can see, the approach is very similar. You just sort and you add and remove, because in this case every time you add the list, because it can be as simple as 1, 2, 3, 1 as one set and 2 as two set. You can actually go through this subsets 2, which will have duplicates. It will be similar to what we have like permutations to. You just sort and then you check the duplicates. The rest of the approach is everything is same for all the problems. So this is what we have seen, permutations. You don't need to sort for normal permutations as long as they're all distinct elements. So you just need to make sure that this element was not already added to the permutation. So this approach is same. So this permutations 2 is what we are actually going through. You can just see you are just sorting, and then like you just seeing like whether you already use that element. It's basically skipping the duplicates, and then add, remove. So there is a similar problem again, combinations. So which will be combination sum. Again, they're just adding one another extra some parameter. As long as you're subtracting and it's not going less than 0, you can continue exploring. I'll share this link, so which I mean, like if you guys have not looked in already, so it's a good reference for all this kind of questions. So in the interest of time, I'm actually moving to the second problem. Merge to sorted list. Oops, let me reset. So this is an easy question. Like you just have two linked lists which are sorted, and you just need to return a merged sorted list. Since like this can be done iteratively also, but for the purposes of today's session, like try to think the solving this problem in terms of recursion. Anybody wants to try this or like explain their approach?
So one thing I could like intuitively think is you have indexes pointing to first array and the second array, two different indexes.
Yeah, this is not an array, but like these are linked lists.
Okay. Yeah, it's the same, like point.
Yeah, it will be similar. Yeah, correct.
Point to nodes, and whichever
you
is
just have a head here, like you can just have current pointers. Yes.
Yeah, pointers there, and is it like merging too, right?
Yes. You know that these are already in sorted, so you just need to merge them into a single list, single linked list.
Okay.
So I mean, like if anybody knows like the merge sort merge approach, it's the same thing.
The iterative way, that is more easier.
Iterative way is easier. Like again, merge sort you can do recursive also, right?
Okay, yeah, that's a different way of thinking though. Yeah. But actually, if you look at like this, the same thing. If we say like the first least node, if it is null, then you return the second one for maybe the first condition, something like that. And then you can do similar for the second condition.
One.
Yeah, right. And then you can check which one L1's value is lesser than the second one's value. And then you can call the merge to least again. This function is a recursive call, sending next of maybe the L1, right? Because that is lesser one.
That is less. Yes, correct.
Yeah.
So else you send the.
Else you send the other one.
Yeah. Yes. You want to code this?
Okay. But I will have to open my.
Do you have the lead code open? I don't know if I can share my. Let me see if I can give remote control. But it will be a little time consuming, I think.
Okay, I'll open my lead code. Just give me a second. And what is the problem number?
21. Like you can use this much.
Just give me a second.
Okay. Yeah, I mean, like the next problem that we have is like an extension to this. So once you code this, we can.
Okay.
We can use this for that.
Okay. Do you
access
want
by
me
number?
to...
I don't know. You can just.
Yeah, I have it open. So can you share me? You'll have to share that.
I can stop sharing, right? And you can
please.
start sharing.
Yeah. So can you see my screen?
Yes.
Okay, something like this. Well, I'm doing it C++, okay?
C++, okay, got it.
L1, I think you say null, and then return L2. Okay, and okay, I'll just say else if L2 equals null, return L1, and then say else if L1 dot L1 dash val right is less than L2 dash val. So I will have to return. I'll have to return list also, right? Okay. Some function here. So here I will actually return L1 dash next. And yeah, L2 will be as is, right? Yeah,
as
because
is.
I'm not
Yeah, because you're not taking elements. Yeah.
And then I can do the other way here, right? Okay. So L1 will remain here, and then L2 dash next.
Have you forgot something?
Oh yeah, I need to return. Oh, I need to return these.
And you need to update the links also.
Okay, so this will be. I'll have to do the same one here, right? Next,
Yeah, L1
this one
next is equal to
and this should be L2 next, right? Next, okay.
And you are supposed to return value. Return the nodes in both the.
Oh, here itself. Okay, for each one will be different. Return because L1 move ahead, L1. Okay. Yeah, I'm returning everyone now.
Yes, so I think it should work. You can just submit and see quickly.
Okay. Okay. Yeah.
I think this is good. So as you can see, it's a simple merge function where we are saying merge to sorted list. Now let's extend the same problem to next level. So imagine like let's get into the another problem. So Santosh, like if you want to try that one also, that will be good. Can you open the handout, the merge sorted list too?
Merge sorted list too.
Someone, okay. Just someone actually is asking the time complexity. So can you explain the time complexity?
Time complexity of this one is going to be O of n, right?
Yes.
Because
So
we are going to
n being the length of, I mean, like the number of
both
elements
of them together.
of the list together. Yeah. N plus m. If n, depends on what you take n and m. If one is m and another one is n, then it will be m plus n.
Yeah.
If you take total number of elements as n, that will be.
Okay.
So someone was saying log n. No, it is not log. It is n because you are just.
Because we are going through each and every element, right? Yeah.
Yeah.
So you are saying the merge case sorted one?
What is that?
So you are saying the second one is the merge case sorted list, right? This one?
Yes. This is a problem. So do you want to try solving this like with a K list? Like what are the different approaches?
So merge case sorted list and return it in a sort list. So you are given this as an input. Oh yeah, that will be slightly difficult, because you'll have to maintain 3 different pointers here, and then maybe if it was an array, you could use something like a priority queue setting, pushing them there, right? And then no, I don't think so. It will be possible now.
So yeah, it's not just 3; it can be any number of linked lists.
Yeah.
So what are some of the thoughts that you, I mean, like you said?
So maybe set 3 different lists, right? So everyone will have a pointer, starting pointer.
What will be the brute force approach? So like, since you already have a solution to merge 2 lists.
So in this case, brute force will be, I can use a min heap, the binary heap, min binary heap. And every time I push all the first 3, first of all, I push that in the priority queue. Whichever is the smaller I pick up, but when I pick up the smaller one, I should know from which list it is coming, right? So I can actually put the next one's list in the priority queue and take that element in the list, and then it can move ahead.
You can add the nodes itself, right? Like the solution that you are mentioning is actually not kind of a brute force, but it's little better approach using priority queue.
Brute force is like we can use the previous approach.
And then like pass every 2 lists.
Every 2 lists, and the result pass with the other one.
Yeah, correct. So that will be the brute force where, but like you need to call the same function k-1 times.
Okay. Yeah.
Because every time you get one output list, and then you use that output to the next one. So similarly, you need to do k-1 steps.
Okay.
So
that would be slightly more work to do than the priority queue, right? So
yeah, that's what I'm saying. Yeah, priority queue is a little better approach.
Easier also, yeah.
So the priority queue approach, is it recursive?
I don't think so. That is what I was thinking was the normal way. So
okay, can you do some recursive approach by utilizing the previous function? Is there some? Can anyone think?
So the brute force way, right? That is the only way you can do.
But still improving upon the previous idea. So just like similar to brute force approach, but what do you pick? Like how you divide the total number of k lists? That's what matters there.
Okay, so whenever you pick that, so your this vector list actually will be modified, right? Because you will be moving ahead in that pointer, and then you pass that whole thing again. No.
So Naga, I won't be able to code it, but what I'm thinking is, like you do for a merge sort, where you basically divide the whole thing and then start combining 2 arrays next to each other, and so the first time it will be like half, and then second time it will be half of that. You'll end up combining half of those, and then half of those, and but again it might be similar to what we did before. I do not know how we. It feels like it is just like the brute force only, so I'm not sure if we are gaining any better complexity by doing this way. I don't know if I made sense. I mean, I'm just saying that use like the first 2, then like 1, 2, like take the first and the second linked list, then take the third and fourth, take the fifth and sixth, and take them in pairs and work on them is what I'm saying. But,
yes.
That may not again. I don't know if that will improve the complexity. I don't know.
Okay, let me try. Yeah.
So.
Okay, if I say something like this.
So it just imagine like the merge sort way. Every time you're dividing into 2, it will be in a similar way. So in that case, it's not like brute force. It will definitely improve upon, because you're reducing the scope every time by half. Instead of in brute force way, you are reducing by 1. But in
okay, let me do the brute force way. Then you can help me if possible.
Okay.
How to make it return.
Yeah, you can just copy the previous implementation for the 2 solution way. I mean, like first you can finish up this.
Okay.
You can just assume that function exists. Yeah.
Okay, is it not okay? Okay. And equal to something like 1. Okay. While okay, right, I'm just taking this one and then I say something in this less than k I is plus is equal to 1 side 2. Okay, I'm just moving by 2 twice of that. And then if I plus interval is less than or equal to k minus 1, and then I call what I should written here. Okay.
Are you trying the brute force one or like using the previous
Something
two
like
list?
this. No, I'm just because I'm just going through this each and every time, right? Okay, in this one, and then I'm actually jumping with this some interval. Okay.
The brute force way would be like every time you start with 1 and you merge the 0 and 1 list,
okay,
and you do 1 and 2 list. So it will be like that actually.
So okay,
I
how
think
do you
you are
want me to
trying.
go?
No, I mean like you only said you will do the brute force, right? So I'm just helping.
No, I didn't understand the brute way how to do that. Yeah, I was just thinking.
So you start with what is this interval?
I was just taking interval gaps of like and keep on.
You don't need to take the gaps. You just have one single for loop to the list to the length of your list. But
Okay.
you start with 1 and you do the 0 and 1. So let's take the size of the list. So k, so I less than k is the length of the list. I don't know what's the C++.
Yeah, k is okay. So then I will be just one, right?
Yeah, it's just incrementing by 1.
Okay, and
this
then what?
k is what? The list dot size, right? Okay.
The list size, yeah.
But you actually you copy the previous code. I mean, like not on this, but the other much too sorted list. You copy this function and the function itself, so you can use it in the other. So yeah, just have it here. So this is actually the solution for 2. So
okay.
So now go to the other function and use the merge to list inside the for loop. And you actually start I from 1.
I from 1, okay.
So you can, or like you can go I less than k minus 1, or like you can do the other way, less than k minus 1. So now you can actually pass the 2.
So list of I, and then list of
I plus 1.
List of I plus 1, okay. And then I actually
you need to call the.
I will have to have a head somewhere, right?
Yeah, so you just have one head pointer, which will take the result of this.
This one, right?
And then you just return that.
Okay.
So this will be our brute force, like merging lists at a time, but like doing the k times.
Okay, I'll see if it compiles. Yeah, it compiled.
So yeah, this is the plain brute force. Like, So now, like only reusing the toList function, can we optimize this instead of a for loop, like every time instead of the next first two, you merge the two lists every time, but in a different way.
So what you are saying? This merge to list?
Yeah, you just do you know the Heapsort like partition, right? Like you can partition the lists into two ways, like every time.
So you find
like
a
based on
keyword for
some
that.
mid. Every time you just take a mid and just like you do the
Okay.
voting part, or
okay, so you're saying to partition it is in a pivot, find a partition and then actually get that partition and then move both of them, right? Okay.
Yes, you can actually do at a time two merges based on like one on the left side, one on the right side, and merge those two.
The quick select one. Okay. Nope. Yeah. So you want me to write a partition here and then
yeah, another function. Yeah, another function.
So list node. It will return a list node, right?
Yes. So that will be the
star, and then you say get partition.
Or just say partition. Okay, you just take the same list, vector list node of list. Yeah. And you have the start and end in this to the array as an input. Start index and in the partition arguments, you can also have start and end.
Okay.
So you use this and divide, I mean, like get the mid as long as start is less than end. You know that it's a valid scenario, just like you do the like binary search, right? Like you compute the mid.
Yeah. Okay.
So
but
now,
then how do we find, okay, this is again.
So the idea is you actually do the two, I mean, like here you call two times. You call the merge to list based on one on the, I mean, like less than start and mid. And then once you do based on mid plus one and the end. So,
but on what basis I call it? What is the condition? So I just compare that with how do I compare it?
No, you call the same list, same partition. Sorry. Wait. Yeah, merge to list. You actually.
So you're saying list and then you start with this one, right? Something like this.
No, this is not merge to list. Yeah, this is correct. But you just need to do the partitioning until you hit the base case.
So you are saying just call partition again, right?
Yes. So, and then another partition from the mid plus one to end. So this both will return the nodes which you are going to merge. So you're basically following like a similar a divide conquer approach of dividing like every time this will be 1 and this will be 2, and you just On this too, you actually use the merge to list. So now you actually return in the next line. Maybe you can just return the merge to list of L1, L2.
Yeah, so this is just the partition, right?
Mm-hmm. Yes.
Okay, so I just call the same thing again here, right? In this one.
I think maybe you forgot one base case here in the partition. When the start equal to end, so you just return. In that case, it's only one list, right? You return that list as is.
So what do I return here? I just return the same.
It'll be a simple list. Yeah, it'll be a single list. So you just return lists of sort, start or end, whatever it is.
List of start.
Yeah, return. Yeah.
Or can I not just return, make the start equal to end and then do that? Is not here itself? That won't be possible.
Or instead of having a if condition, I mean extra if, like after a if condition at the end, you can return, right? I mean just.
Okay, you're saying this way. Let's see.
So now you just remove this for loop and call the partition. With partition of list, comma 0, comma list dot length -1.
List dot size.
Yeah, sir.
-1. Okay.
Yeah, that head you need to
assign to the partition.
Yeah, this will be the result. Result will be your head in new head. Okay. So it should work now. Oh yeah, I think the way you can actually do something. So if you can pick the condition, if start is greater than end, you just return null.
So here I just return.
Just remove this.
That return statement, you can just add it there. Yeah, return.
Yeah, you just say return null. Yeah.
Or you can say return list of start there, and you don't need that first condition.
But what if the start is greater than end?
In that case, yeah, I think since you have those two conditions, you can just return null. That should be okay.
Yeah, it works. I don't want to
So,
submit it because I'm sure it won't not going to work on the test case.
I think it should work. You can give it a try.
Oh, it works.
See the time difference.
Yeah, time is 32. Yeah, or else
so it will be. You can also, if you would have submitted the previous one, it would have taken more time than this.
Yeah.
So
yeah, absolutely.
The complexity, since you are dividing every time the total list like into two, like the total merge scope will be reduced. Like if you have 8 in the first steps, like next you will have 4 lists to merge. Whereas in the brute force approach, it will be reduced just by 7.
Yep.
So here, since you are dividing, I mean, like it will be a faster approach.
Naga, there is a comment to basically summarize this approach. And if we can talk about time complexity also, it is less, but how much it is?
Yes. Santosh, you want to try finding the time complexity for this? You have k lists and what you are dividing every time into half.
You are dividing, so that would be log n, right? So you are dividing by 2.
So which one you are dividing by 2 every time?
Because you are finding the midpoint, right? So you are dividing the
length of the, I mean, like the k is the list, right? K is sorted list. So the k thing you are every time you are reducing by 2. If you have 8 lists to merge, so our partition function will actually first time go to 8, next time it will come to 4, next time it will come to 2. So this partition will be log of k times, and the merge thing you need to do.
So merge is only once, right? So
the merge you are still doing on every list, but the total number of elements will be since the merge will be based on the total number of elements combined. If we take all the sum of the elements across all the lists is n, then it will be n log k, I think, if I'm right. You understood what I'm saying? Or
so log k is for the partition.
And for the merging, you are merging n elements, right? N elements which are spread across all the k lists.
Yeah. Okay. I'll go to
Isn't it coming up with the complexity will be a little bit more complex in this case, because you really don't know which list going where, right?
Which list?
Each list can be of different length. So when we say n log k, n is the total length of all the element, final result.
Yes, I mean like that's as
for
a
all the lists
combined.
together,
Yeah, I wanted to tell as a combined, right? So n is the total number of elements. That's in the worst case, like whether you take, I mean like if we take list by list, the elements will differ. But since we cannot determine since they are not of even length, we cannot put the time complexity in terms of the length of the list. So we can just say that like since irrespective of the individual list size, since we'll be merging all these list elements together, whether in like step by step, the total number of merges will be n, if the n is the total number of elements across all those k lists. And the number of times we are partitioning or like doing the merge operation is
log k.
Log k.
Okay.
And for
but
the
in the brute force approach, it will be k times
n
minus
into k,
1.
right?
Yeah, k minus 1, it will be like k only.
So brute force would be, sorry, say that again. Brute force would be?
Like if you have k list, you are doing the merge k minus 1 times. Minus 1 is negligible, so you are doing like k times merging. So merge of two lists will actually, so merging is anyway n. So the k is the number of lists.
So basically that would be n into k.
K, yes.
And if we now use priority queue in this, then probably it would be k log k.
No, it will still be n for the merge, but you are using the extra space for priority queue, which is k in the worst case. Yeah. So yeah, in the space of priority queue you are using. So the space complexity will be additional, but the time complexity I think is again.
So the time complexity should be O of n, right? There in the merge sort.
Hey Santosh, can you tell your priority queue and Heapsort approach, just the approach?
The priority queue actually.
You just add the. I mean, like it will be. Yeah, you can explain, Santosh, since you already.
Oh yeah, you can go. Yeah, what I was saying is every time you pick up first element, so if there are 3 lists, so I'll pick up first 3 elements and put it in a priority queue.
First element of each list, not just
first element of each list. Yeah.
Then and you know which one is minimum. Yeah.
Yeah, and then put that in the main list, and then wherever it came from, you have a pointer to that list. So you can take the next element from that list and put it in the priority queue. And so as and when you pick it up, when the priority queue is empty and the lists are also empty, you can return the header.
Okay. Thank you.
So since the priority queue also returns in log terms, so the time complexity, I would say, I think it will be similar for the same, but except that the extra space you are using for priority queue, but not here.
So this is more efficient, huh? N log k. That is also N log k.
So. Yeah, that is also N log k. I think your priority queue is also N log k.
So definitely, I mean, I have some disagreement here, but I don't know how to prove it. Yes, with the priority key, it will be n log k. It's kind of like merging n sorted array, right? Exactly same. But with this approach, I think it should be more than n log k. If both have same, that means, go ahead.
Yeah, I mean, like it's. I think it's. Can you go to the solution, Santosh? I think I think I saw the time complexity is there. So can you go further? Like, so this is 1 by 1 brute force. So this is optimization by priority queue.
So priority queue is
N log k. So you are taking the space of yeah.
So this is merge list 1 by 1 and merge with divide and conquer. So this is what
this is the divide and conquer.
Okay,
yeah, this is what I'm talking
divide and conquer. Is there a priority? Sorry, complexity for that?
Yes, it could be.
Yeah, it is the same. Yeah, N log k.
Okay. Yeah. So it will be. So if you see the Bhavesh, like your the partition function, if you want to express in terms of recurrence relation, it will be 2 into t of n by 2. I think so. You are dividing every time by 2, and you are calling 2 times. So if you represent this in terms of recurrence relation, you can, I think, usually try to come up. This merge is actually whatever the length of that merge scope, and that L1 and L2 length, and this partition is expressed in terms of same thing. So 2 n by 2.
So it is t of k by 2 plus n, right? That if you put that recurrence.
Yes.
So if you can go to that, can you scroll a little bit up where there is a diagram? Here only. Yes, there's a diagram for this approach, right? A little bit up. Yeah.
Little bit up. Yeah. Okay. Correct.
So see, now list 0 and list 1, right? So if suppose numbers are equally divided, then I'm okay. If number are not equally divided, for example, list 0 has the most number. Okay. So when we merge list 0 and list 1, we go through all the elements.
Okay. Yes.
And when we do the list that 2 again, the list 2, we go all the. Okay.
So it's basically you have 2 steps, right? For merging, in the worst case, you have to merge all the elements irrespective of whatever the approach.
Yeah. Makes sense. Okay. All right. Yeah. I think just the time check. We have 2 more problems now remaining. I'm not sure how much we can cover, but I think we should move forward.
Yeah, at least like if we cover 1 more problem, that will be good.
Yeah, I've stopped the sharing. Yeah, Naga, go ahead.
So let me see. Oh, I think I need to share again. Where is the share?
So Praveen, you were asking about summarizing this solution. Did you get your answer? Okay.
So the next one is you convert the binary search tree to a circular doubly linked list. Let's look into the examples clearly. Again, it's clearly binary search tree. That means that it is, it is like sorted elements in order. So you can, we need to convert to a doubly linked list, but still it should be in sorted from starting to end. And they're asking to do in place. So it's basically, as you can see, 1 to 2, 2 to 3, and 3 to 4, 4 to 5. And then like once you link all of this, they're asking to link the start and end also to make it circular. Since it's doubly, like you have pointers both different in both directions. They're just showing the linking approach. So these are some other examples. Anybody want to give it a shot or explain the approach? Any volunteers? Any traversals that you can do? Like,
I think it should be doable by in-order traversal.
Yeah.
But the main thing is we have to somehow track the first and last one so that we can link that together, and we have to also track the first because that is the one that we have to return at the end.
Yes.
Otherwise, it should be simple in-order traversal where four. Suppose we start from the 4. The left would be whatever the result of we are getting in-order traversal of the left side. 4 right would be whatever the result we are getting from the in-order traversal of the right side. And I think somehow we have to track the 1 so that we can return, and also track the 5 so that we can link 1 and 5 because we have to make it circular.
Yes.
So that's probably can be high level.
Tracking 1 and 5 is more like tracking min and max, right? Just min and max.
Yes, correct.
Yes, that's true.
So
there is no duplicate, right, in this?
Yeah, no duplicates. It's BST, so we can assume, I mean, like at least no duplicates in the given problem. All are unique. So at least like someone gave a clue like tracking min and max in the in-order traversal should actually give which one is the first and last nodes. So anybody wants to give an attempt of solving this? So yeah, in-order traversal should work, except that you need to keep track of like along the way what is the current links. So in the in-order traversal, you just need to keep track of the last node, so you can link that efficiently with the current node.
Oh, which one we process the last?
Yeah, so if you go to 2, you should know that this is the last thing that you processed.
I see. Okay. Yeah, that makes sense.
And by the time you finish all the traversals, the last will become this, because you would have finished a traversal. Is the approach became clear for everyone?
Yeah, I think it is.
Anyone wants to try coding? So yeah, anybody volunteers? It should be like in order traversal, pretty simple. Anyone wants to attempt and get practice?
If no one is trying, then I can try. Otherwise,
yeah. Let's give it, see, another 30 seconds to see if anybody is approach clear to everyone, or like any questions on the approaches.
Can you explain the approach again? So I got that in order traversal is like left, root, and right. So we will reach up to the 1. 1 will be the leaf, and then we are going to go to the
So basically the idea, since they are saying that we need to link the first and last to make it a circular doubly linked list. So we need to track at the end of the day, like at the end of all this linking, we need to track which one is the first and which one is the last. So tracking the first one will be like if you go more towards full left to the deep, whatever you get the first element in the in-order traversal, that will become your first or left or whatever you call it. So in the same way, whichever you link 1 and 2, suppose I visited 1 and now I made like my first and last as a 1, and when I go to the 2, because in order left, root and right, in this time my last is 1, so my current is this 2, so my current dot previous will become last, and then you update the last 2, and then you visit the right node, which is 3. In this case you actually link my uh, this dot previous to last, which is 2 in this case. You have both way linking here. So after 3 in the in-order traversal, since you completed this whole subtree, you go to the root. So which is last? Is the last as per the updated. So we update 4 dot previous or whatever the left to 3, and then you make the 4 as the last. And then you go to the 5 as per the in-order traversal. So this dot previous or like left will be this 4, as this is the last at this point. So and then you update the last to this. So now if you are out of the in-order traversal, you know that like you have this as a first pointer and this as the last pointer. You just need to link these two and you are done.
Yeah. Okay. Yeah. Thanks.
Do you want to attempt code? You understood?
Not now. Yeah, I understood, but yeah, still like trying I'm still on easy questions.
Okay, I'll try then. No problem.
Okay, go ahead. Let me stop sharing.
So this is just that in order survey, right? Okay.
Yes, yes. Convert circular. Can you type convert? It should in the problems. I can ping you the link if you want. No, just type convert in the top. You should get the link, or I can post this.
I think it's 426, right? Okay.
Yes, yes, yes.
So if root equals null, return null. Okay, or else what? Return in order root. Okay, and then you were saying I need to take 2 nodes, right? Node 1.
Yes.
Node
So basically, whatever you want to call first or last or whatever.
Last, okay. And then do the in order. Order, okay, and then node star is RT. Right, and then if RT equals null, return null. Right, and then or else in order RT dash left. And then in order RT dash Right. And then if you say, what you are saying about this one?
So
if the last one, right? Okay.
If
So if I say
last, if the last is equal to null, then you just make it as first and last same, right? For the first time.
So just make it first equals last, right?
Is equal to whatever the current root.
Oh, so the RT here, sorry. Or else it will be, I need to make the last left will be equal to, oh no, so last right right will be equal to the current root, right?
And the other way,
then the RT left will be the last one.
Last one.
That's all.
Yeah. So now this will actually do all the linking, but not the first and last. To make it circular. Have you forgot something? Where are you updating last?
I need to return the RT here, right? Because
no, you don't need to return. So, but before the in order of write, do you need to update something like after that else block? Where are you updating the last, the current visited node? Every time, whatever the node that you are visiting in the in order, your last should be pointing to that root RT.
Last is equal to RT here.
So that next time, the next traversal node, this will be the last. This will be the previous end of, yeah. So now this will do the linking. So, but in your main method, you just need to make sure the first and last are linked.
First will be linked to the last one.
Yeah, first left will be the last, and the last left, last right. What is it?
Last right, and last right will be the first. Okay. Yeah, so this is what it is complex. Okay.
Try running. What happened? So you are not returning the first.
Okay.
Okay. Understood. I think we are out of time. So I don't think we'll be able to get to the last problem, right, Bhavesh?
Yes, I think we can end it now, or we can if everyone is okay. If few people want to continue, then we can continue solving that problem. Because anyway, while uploading, we have to edit out this problem, the one that we just discussed, because it's paid, it's accessible to only paid user. So we'll not upload that portion. Is the last one is also a paid problem, or?
Oh, do you mean like we cannot do this premium problems?
Naga, some problems are accessible. The questions themselves are accessible only to paid users. So this seems to be one such problem, because I am not a
Oh,
paid
yeah.
user. I'm not able to access. I'm not even able to see the question.
Oh,
So
okay.
We can
So
discuss.
should we not do these problems
No,
like
no,
in
no, no.
these meetings?
We can discuss. We won't be able to put it on YouTube, that portion.
Oh, okay.
Yeah.
Got it.
So basically, mostly all the session, whatever we do online, we post on YouTube channel as well, right?
Yes, correct.
Yeah, we'll edit that out. That's not a problem.
Okay. Yeah, thanks for pointing that out. Next time
Yeah.
I'll keep it in mind.
No, that's fine. Yeah. Is everyone want to do the fourth problem also, or can we just quickly talk about approach for the fourth one, Naga?
Yes. So let me share my screen and. So everyone see my screen now? So last problem is about like we already seen like a similar problems where you find that like given this parenthesis combination, find whether it's valid or not. We know like we have multiple approaches to solving that. So this is a little trickier one. It's one of the hard problems, but like where they try to give one of the braces extra, and they ask you to generate all possible valid combinations of that. So the approach for this one is like as you can see, you have every pair of open and closed parentheses. In this closed parenthesis, whenever you see, like in this case, you have an invalid closed parenthesis. So the idea is that like wherever you have the closed parenthesis, you attempt to remove that and see whether it forms a valid combination. It's kind of backtracking, but like if you can do limited backtracking instead of removing and taking every possible combination, you can just trim that backtracking and focus only on the whichever is making it invalid. So in this case, closed parenthesis is making it invalid. You can actually check the count, right? Whether open, close count. And like since in this case only closed parenthesis is like little extra, you attempt to remove this one, and that will be one combination, and you attempt to remove the previous I think, I don't know, one of this one. So there are two possible combinations. So similarly here also, like you try to remove and see, like I can actually quickly show the code and explain. So as you can see, like I have the remove function where I'm accepting the original string as is, and then the list of valid results, and then this last I and last j are two things which I'm actually tracking. So if you see, like I'm actually looping through this the array and counting the closed and open and closed parentheses, that is this and this, and as long as the both are valid, which is the case in this, we will continue. If it becomes invalid, so in that case it will be negative, we will come and see, we will attempt to remove which from the last starting invalid position we just or last visited, which making it invalid. You just try to remove each character and attempt to call itself. And if it's not invalid, which is not visiting, so if all the combinations that we get into this substring recursively are valid, then it comes to this loop. Then you actually do the same thing in a reverse way, because it could be possible that there could be more number of open parentheses than the closed one. So in that case, we can reuse the same code by just reversing the string. And this time, So in this parenthesis, the first one will be a closed one, and this one will be an open one. Same thing. The idea is you just reverse the string and check whether you have again invalid open parenthesis or not. So once you finish both the loops, you just add the result back to this result. This is kind of limited backtracking because you are just checking the invalid combinations. Here, if you do for every possible combination and then you check whether it's, then that will be full backtracking approach. I can post this solution so you can go through. There is somebody who has put like a similar approach from where I inspired this. I'll give that link also.
But do we really have to count here, or without counting also can it work?
The counting will actually make limited combinations. Otherwise, for every, it will become 2 to the power of n. So for everything, like you just check whether you want to include this or exclude this in your final valid combination. For every parenthesis, you have to make the decision whether include or exclude in the result. In the worst case, even in this scenario, it will be 2 to the power of n, but like you are reducing some complexity by counting.
Okay.
Okay. So with that, like we can end because we are almost like of time. I think this is more asked in Facebook. I think invalid parenthesis.
Okay, Naga, where, there are people asking about this recursion document that you were sharing.
Yes, I will export that and upload in GitHub or GitHub. I meant to upload here, but I think I have my branch still open, so I'll upload this document also.
Okay. Right.
And share the link in our meetup info Seattle Slack.
Yeah.
I think Slack should be okay. Much easier.
Okay, that's all. Thanks everyone.
Thank you. Thanks, Naga.
Thank you, Naga.
Thank you.
I'll stop sharing. Yeah.
Thank you, Naga.
Davesh, have you ended the